Hey guys, so in this video I'll be talking about regularization and specifically L2 regularization, and I'll mention L1 regularization in a bit. So starting off, L2 regularization encourages smaller weights by adding a penalty to the loss function when the weights become larger. This might sound complicated, but I'll go over more details in a second. So L2 regularization adds the squared magnitude of coefficient as a penalty term to the loss function. So the weight value squared. And this term is multiplied by a hyperparameter known as the regularization strength, and this is often denoted as lambda. So the value is chosen based on the amount of overfitting in the network, as well as many other factors like your other hyperparameters, your learning rate, and so on. So as you can see, the extra term is added to the cost function, and it's called a regularization term. So here you've got your regular cost function, where it's like checking how good your network is doing, and you add this regularization based on the magnitude of your weights. So in L2 regularization, it adds the weights squared, whereas in L1 regularization, it just adds the absolute value of the weight. So we'll see how that affects it in a bit. Regularization makes it prefer smaller weight values, while allowing larger weights only if they considerably improve the first part of the cost function. So regularization is a way to find a balance between small weights and minimizing the original cost function. And its relative importance depends on the value of lambda. So a small lambda prefers minimizing original cost here, whereas a large lambda prefers small weights. So I found a good image that visualizes this. Here's the source if you want to look it up. So here, this is what would happen if you want to minimize the weight values. So if you want to get the smallest weight values, it wouldn't really do anything. And at the same time, if you want to get the minimum cost, you would go to here. And this is kind of a visualization of the gradient decreasing as you go through backpropagation gradient descent. And so we want to kind of find a balance here where you haven't fully minimized the cost, but you're still keeping it and you're still keeping it quite simple. So this simplicity we'll see in a sec is the key to decreasing overfitting in these neural networks, and it's the main reason this L2 regularization is used super often. So another way to look at it is if you've got this these data points here, this is like a good estimate of like the average amount, but this is if your network continuously trains on the data and begins to overfit because of this random noise. So this random noise isn't actually useful, but the neural network is learning these random bumps and stuff, basically. So this is what L2 regularization gets you to do. L2 regularization leads to less overfitting. The main idea many papers have discussed about why it works is so the human brain has many more neurons than these artificial neural networks, but it still doesn't have the problem of overfitting, and it can recognize objects from only a few training images. So these problems won't occur if you have a simpler network, one with smaller weights. So a simpler network, like using the sample of recognizing handwritten digits, learning random noise would cause the network to improve in recognizing training data because it memorizes small details, but it decreases the efficiency in recognizing new digits that are drawn slightly differently. So by making the network simpler, you're not letting it learn the tiny details, the tiny noise from training data. So another note is that regularization doesn't constrain biases because the biases allow the network to learn from random noise. So they can be as big as they want or as negative as they want. It'll affect it positively if they're large because they allow more flexibility in behavior, and they just allow like interesting behavior. So L2 regularization on the MNIST network. This is just a quick graph I made up. You can see if the regularization strength is way too strong. That's the blue line. It obviously doesn't converge very high. Um, sorry. Whereas all the other values here, they converge at a similar amount because the regularization is applied to like a very small network. This network only has like a few hidden layers with like not many neurons, and this was trained for about an hour on my laptop, so that's the only reason these don't really show huge improvements with L2 regularization, because the green one should in theory be lower. It is lower technically, but there isn't much of a gain here. And L1 regularization is different because it shrinks the weights at a constant factor, while L2 shrinks the weights proportionally to the weight value. So this results in L1 decreasing large values less than L2 and decreasing small values more than L2. So L1 has many weights close to 0, with a few important weights having large values. And this is an image of L1 regularization. So that's pretty much it. Thank you for watching and have a great day.